Yeah, thanks for coming. I'm Dan Helmick, work at Samsung. I was reminded before I got started that I have my Ursinus bow tie on, so if anybody's even heard of Ursinus, I'd be curious to chat later. Pretty sure it's a small college not many people have heard of, but yes, I'm going to be talking about SSD virtualization. Really, it's about sharing SSDs. Normal agenda, give you the background and get into some of the use cases is where I'll focus, and potential future directions, which includes hopefully a discussion. If you guys have any ideas, I actually would love to hear that. From my own perspective, so again, just better defining what virtualization is. For me, it's kind of presenting the stored data with access attributes that differ from what might be initial conventional access. So something that can be virtualized are PCIe layers, NVMe controller and identifying data. You want to also sometimes separate where data is placed, which is a form of virtualization. You're really having a placement separation. Storage administration, log pages. I think namespace is a type of virtualization that's long-standing, and then security boundaries as well. It's really enabling a limited or replaced view of storage access and enabling that sharing of storage. And some of the motivations here might be a large capacity SSD, limit the SSD command availability to unprivileged users. We might isolate the performance impacts from several storage users. This is the data placement coming in. We would possibly want to sandbox some bad actors to limit their data access, which folds into a confidential compute enablement. And I think that we might, another more grounded example is making a new SSD perform similar to an SSD that it replaces. Through this presentation, I use the word tenant. For this presentation, really am defining a tenant to be extremely generic, and I think that this kind of extends the applicability of this discussion when you realize that you could have many diverse different software tenants, from a software process to an application, container, VM, or you could have hardware type identified tenants where you're talking about a CPU processor, a CPU core thread, maybe an FPGA or GPU. Or maybe even just a partition of a GPU, right? A portion of it that's working on the inference when the rest is working on the training or something like that, right? So I'm on purpose being just as generic as possible as what a tenant really is, and that's why I use that word. Some things that, I'm Samsung, so I'm Samsung focused. And so I really am kind of like focused in on a few different features that we at Samsung have been focusing in on. And I wanted to call attention that virtualization is really an ecosystem effort. And I just here am calling out things that were either done long-standing virtualization capabilities, or maybe they were things that were developed in parallel by other focused players, even though we support them as well. So there's things in the PCIe layer like dual port, SR-IOV and TDIS for security. And then NVMe has already had primary and secondary controllers. And I think NVMe over Fabrics has a lot of capability where they've been virtualizing in that software layer long-standing. So being an SSD-focused architect, I'm focused in on those SSD features. I'm going to focus in on this one example of virtualization because it kind of knits together a few things I want to get to here. So this example of virtualization is a VMM, a virtual machine manager, that has several virtual machines on it with admin queue and submission queues that are to the VM. It's inside of their purview of their world, and I show that encompassed. And this VMM, the virtual machine manager, has created these software boundaries, to hide the VMs from each other, and that's something that I believe is long-standing. So they end up creating this curated view of any registers, that they present to each VM, and it can be a different representation that they give a different VM. Potentially one VM is legacy from the 80s and another is one that spun up yesterday. So they can have a curated view that's very different of what they present to those VMs. From this VMM perspective, the admin commands will come in and they have 3 major different paths that can be happening through the VMM. There might be a local response from the VMM. For example, responding that there's a capability not supported, even though maybe the underlying SSD does have it, but perhaps it's not available in the whole fleet. So they pretend like it's never available to this particular VM. Another potential is the admin commands get passed through. And I think that there's another that's a little bit more interesting is where a filtered pass-through may happen. There might be a query of news to see the usage of the drive, and it might actually send that command to the drive, but then curate the response to be slightly modified for what it wants to present to the VM. So there's a whole host of what a VMM may do through different commands and use cases and their goals. I/O commands, they're normally a little bit more, so they can similarly have the local response, pass-through, and filtered response. But more often, I think the most common thing for VMMs is to just intercept the doorbells. And because they're intercepting the doorbells, they have the possibility of inspecting and doing things, but for the most part, they receive the doorbell and echo the doorbell to the drive. So a little bit more of a pass-through on the doorbell in order to still send those commands to the drive. So the advantages of this kind of software virtualization is that we get virtualization enabled, right? I think that VMware really kind of took off and had a whole business model around this. We can also update our virtualization, right? So we have more exotic and advanced features, like perhaps we want to enable some VM encryption or any other thing that gets brainstormed up. So this is really great for prototyping and growing and evolving. But the challenges are that there's software layer that consumes some CPU cycles. And there's some delays for perhaps even the doorbells. I just gave an example where the VMM must receive the doorbell and then recognize it's there and echo that doorbell into another position where the drive actually picks it up. That's got a delay as it interrupts the VMM and copies it over. And then there's always an attack vector. Depending on how you view security, potentially you view the VMM as an attack vector for bad actors if they were to break out of their VM into the VMM. But generally speaking, confidential computing is not compatible with this software layer because it's able to inspect and see and interact with that VM. The VMM is able to interact, inspect, and work inside of the space of the VM. And so that's orthogonal and not desired for confidential computing. They want to encrypt everything and not even allow the VMM to be able to view inside of its, what it's computing on. And then finally, the SSD has no knowledge that it's being virtualized in this world, which is great because you can use any SSD. It's great for that software ability to play in the playground. But at the SSD layer, we have a loss of differentiation between the tenants. So we are not able to best support the goals depending on what you want to do with these VMs. So I'm going to go through a few examples here and talk about how giving more knowledge of who the tenants are to the drive enables better virtualization and better reaches those goals of the host. So moving to SSD improves our performance latency, and it also allows those stabilized virtualization needs to be hardened in hardware, and the security requirements are increasing, and I see that confidential computing move to hardware, and I see that continuing to increase there. I don't see that backing off. I'm going to speak through 4 different major features here And I called out their NVMe TP numbers. So FTP, and then also tracking LBA allocation. And then there's kind of two things here where I've called out the TPs. There's like a migration of the data and also the migration of the controller. So I've kind of separated them, even though they're kind of grouped differently in the TPs of NVMe. All the information in 4193 hasn't been ratified, so I just used the information that was already publicly available for FMS. And actually, I have a call out later, but Lee Pruitt and Mike Allison have already presented the most recent information, more recent than anything I put in here, on Monday morning. So you can find the slides and the recording on the website. But they gave a much deeper, better update there. So how do we use FTP for separating tenants? We would have, for example, one reclaim group that I have drawn here, and we can initialize that. We can have the admin commands path where we have a VM sending a create namespace command. The VMM captures the command, populates a default placement handle with reclaim unit specific for this particular VM. And now the VMM is able to send the admin command to the SSD, and we can now have a namespace with a default RUH that the VM0 is not aware of, and it's been set up to have that RUH assignment, and now that namespace for that VM will be placed on RUH0. You can do this for every VM, and I have shown over here on the right side, we have VM7 is actually getting multiple namespaces. We've given all of those namespaces the exact same RUH, and so that VM, over all of its namespaces, is still using one RUH and is separated in any write amplification that it's going to be experiencing here by the different RUHs. So we do end up with separation of the write amplification of the tenants. And now every tenant, if they are so inclined, they can choose to optimize their write amplification. You could also have a scenario I didn't diagram where maybe VM7 has namespace 4 that it's going to be a circular buffer. It's possible for the VMM to be intelligent and provide a different default RUH for that circular buffer namespace, right? So it can have, again, two different separations even within a tenant. So there are a possibility of accelerating sequential reads and writes because they get placed sequentially and read sequentially. And we can, of course, get the trims accelerated similarly. So big deallocates will be less impactful. One thing to call out with this, though, when we get down into the nitty-gritty of what FTP means inside the drive, we can now look at two example tenants. These are writing circular buffers. And so they have write amplification of 1. And this is great because we've got them separated. If they were writing them together, they would look random to a drive. So we've solved that. Everybody's write amplification of 1, so the drive overall is going to have write amplification of 1. If we throw in a third tenant into this situation, though, we now have that tenant doing random writes. Okay, great. Again, we separate that. Only the RUH3 traffic is random and going to need the garbage collection. From a reads perspective, I think for all three tenants, good news. Most everybody in the ecosystem, all SSD vendors, prioritize that read tenant. It's going to suspend any programs. It'll suspend erases. That read is going to get done very quickly across all of the SSD vendors. I think that's a pretty pervasive statement there, that reads are very well accelerated. So we're focused in on the writes. From a write state perspective, we achieve max performance per tenant related to the write amplification if everybody else is idle. What do I mean by that? So what do I mean by that? If we look at traffic that's mixed in a time and we have an over-consuming tenant, then it reduces what's achievable for a different tenant. So we can look at just tenant 1 doing activity. Maybe tenant 2 and tenant 3 are idle. With tenant 1 doing the writing, we're going to have 100% sequential write performance out of the drive achievable. But when we now have tenant 2, they're both writing sequential, but suddenly we have half the sequential write performance achievable from the drive. And that's noticeable at the tenant level. You can see that performance change. You're sequential, you aren't having write amp, but you've lost a throughput on your drive. And when you take that, add that random writing tenant number 3, that tenant 3 is going to swamp the drive without any other control. And so tenant 1 and 2 will now see, depending on the drive, 10 to 20% of their sequential write performance. That's very noticeable to an end user. And so the end conclusion here is that, yes, we have the separation of data that's separating the write amplification of the tenants. And the tenants now have the ability to optimize their write amplification, but without some later limiting of the media access time, we have an incomplete tool set to really do everything we want from a performance impact of those end users. I'll come back to that a little bit more later. When we focus, let me transition a little bit more back to the example. We have a data center with many VMs deployed, and we want to have live migration of a VM enabled for the data center. We might want to redistribute system load, root around failures. And of course, an ideal is that the VM is unaware the live migration is happening. It doesn't want to be aware that it's being virtualized at all, ideally. So we have this source system where we have the VM running, shown in orange. And we're using, in this example, SR-IOV with primary controller being managed by the VMM. So the parent there is on the primary controller. And secondary controller has the VM on it. And this is just one virtual machine, but of course there's going to be many VMs on that source host using that source SSD. And now, in this example I'm getting into, the VMM decides that that particular orange VM needs to move. So it's going to move over, ideally, to this target. Similar setup. It'll be a mirror kind of setup. We start with a pre-copy phase with starting of the logging here. And so race conditions are a concern, and the live migration TP is resolving them. It's allowing the VM to continue to operate. The start logging command comes in from the parent, the VMM, and eventually that drive is going to begin doing the logging. We don't know exactly precisely when it'll start logging relative to the VM's ongoing activity. It's allowed to do any interactions. Eventually that logging starts, so now we have diagrams, a command that came in from the VM, and the logging went out, right? So the commands came in and out of the secondary controller. The logging goes to the VMM through the parent. We do have a question on when that happens. So you have two diagrams, IOs, some that may have started before the start logging was sent to the drive, and others maybe just don't have a clarity on where they are relative to the drive starting their logging. But eventually, the drive recognizes the green IOs here is the SSDs recognize that from now on, every command that is pulled in from the drive or that is already in flight, from now on, it will be logged. So it's able to send a logging started response. This is completion of the logging commands. And now every command that needs to be logged will be logged. The VMM has successfully started that logging in the controller data queue. And any unknown commands, good news is that the completion has solved any race conditions. You know the boundary condition there. So the prior commands in flight have finished, and any future will be logged. We want to now set up some of the controller and use that infrastructure to set up that controller. So again, I have it here, the title of the most recent information from Monday's presentation. Very simply stated, we have an initial system. I'm showing the target host and SSD with a controller G as the parent, and then we have an underlying controller P and namespace X. So we will use the infrastructure through this TP to create an exported subsystem, and we associate the controller and namespace and show them in the exported, as an exported controller and an exported namespace. I didn't put this detail later because I ran out of drawing room, but propagate this information to later slides. So now we have the exported subsystem with controller H and a namespace here. And we have this precondition coming into the situation where we have a target system where we'll have space for a VM that'll be migrated over. We can use the VMM to set up and initialize any admin queues, read-write data, I/O queues that's needed. And these are one illustration here. You could also go through a shared namespace through the VMM as well. All valid ways of populating data. This is we have a namespace. This namespace happens to have a very sparse amount of data. So we can see the amount of data inside of this namespace. It's only the black. So we don't want to copy the entire VM namespace when it's so sparsely filled with data. That would be a lot of moved data for no reason. It's a lot of trimmed, deallocated data. So here we're able to do a query using the LBA status per granularity. We can query that namespace data mapping. You're able to see the granularity. And we as a drive, anytime we have any data other than deallocated, we will return it as mapped. So that includes read uncorrectable. The VMM is able to see, all right, here's a group of 3. I can read those all 3 together and get all of that data that's shown with the brackets and so forth. So it's able to get any granularity that does have data. And of course, setting that granularity is customer conversation on what you want to see for that response, right? It can be more efficient with bigger granularities, but then you lose the efficiency on what's transferred. So I diagrammed what might be a namespace mapping down here in the bottom, source SSD. And we're able to get that granularity reporting where there's data to the VMM. And it's able to submit each of the reads and move them over to populate the namespace Y. You'll notice that I have the VMM is able to know the granularity of that source SSD. Over here on the destination target SSD, we've lost that, but it's not important. We're getting any potential data written from the host. So back to that logging, we do have the controller data queue receiving the log entries. It's been getting that while we've been migrating and populating the initial data for the target SSD. And so now it's populated, but we have to catch up. So there's going to be, the VMM is going to go through the controller data queue. It'll see what needs to be moved, and it'll read in from the source and write to the target. I see a question. Yes?
So just to clarify, who's doing this background copy? Is it the orchestrating VM?
Yeah.
And is it accessing it through which name, what namespace is it? I mean, what controller is it accessing?
Thank you. So the question is, what are the active parts on this slide? So I'll go through each of the parts. Okay. So
in particular, the one that's doing the background.
Yes. So the VM is locally working with its controller Y and namespace. The VMM is the one receiving the logging for what activity is happening over on the child. So it's receiving that, and so the VMM, through potentially a shared namespace, is able to do direct reads from controller X down to the namespace. So it depends on the permissions set up from controller X on accessing the namespace, so there is a dependence there. I didn't call that out. That maybe is why you stuttered and asked the question. So it's, assuming in this example, a shared namespace, so it's able to read and migrate the data over. And now again, through either the initialized I/O queues that I showed on a prior slide, or potentially through the destination VMM, it's able to write to controller G to a shared namespace Y. Again, two solutions that are acceptable there, especially since the target SSD does not yet have a VM there. We can configure followed by deconstructing. So a couple of solutions are available, and hopefully that answers. Okay, thank you for catching me there, though. Okay, I think I just done that slide. Yeah, let me just make sure, just pause my, yeah. So the data is able to be copied in an ongoing manner, catching up, right? So the CDQ continues to get longer. The VMM is gonna come in, chew through that CDQ in loops, and eventually it'll be catching up, and there'll be shorter number of CDQ entries as it catches up. Oops. Okay, so now we have the VMM, it caught up sufficiently close to where the CDQ entries are quite small, or zero, hopefully. And now we do a stop and copy phase. So potentially that VM is still doing interactions. Those interactions continue to get logged. We have the VMM makes this decision, now is the time to actually do the migration. So it sends in a pause. Again, we have that VM potentially continuing to send the IOs that are getting logged. So we have this stop fetching action from the SSD, right? So the VMM is sending that information to the primary controller. The primary controller is stopping the secondary controller from doing any fetching. And so at this point, we want a situation where all completion queue entries end up being completed and onto the CQ, right? So whether it's an error or a success or failure, we want that to reach all CQEs to reach the completion queue. So now, potentially, because the VM may not be paused, the VM might be continuing to accumulate more in the submission queue, we've stopped fetching, so it's growing potentially. The CQEs are all ending up on the completion queue, and there's nothing in flight inside the SSD with respect to the secondary controller. There might be some long-lasting commands that potentially take a while to complete. When the primary controller recognizes nothing else is in flight, at this point we return and say we're paused, right? So we complete that command. The pause may also hit the CDQ as well. So everything is on all submission queue and completion queue entries are on their respective submission completion queues. We as an SSD, source SSD, we need to be ready for a potential resume command that may come in. This could be a system error because things are hard for hosts, they have errors. Never happens in an SSD. But ideally, we want the source and the target SSD to both be ready to be restarted, depending on what's needed from the host perspective. The VMM, I'll show this a little bit more, but they parse all remaining CDQ entries, and their next job is to copy the final data over, right? So I show that here, same process, it's finishing the CDQ, parsing, and at this point, it's able to get the NVM subsystem state through controller X, and it's able to set that state through controller G. Again, details from Monday's presentation. And similarly, using the controller state, it can migrate by get and set of the controller state shown here. And the VM is migrating from the source host to the target host. If you are using temporary admin queues and IO queues, you would need to make sure that they're configured appropriately. So again, just visual view here. We need to be prepared whether we're the source of the target for that potential resume. And of course, nominal NVMe flows for cleaning up afterwards. So from a perspective of what is there already from a TPs that have been in migration covered those, but I think that there's some imminent improvements, right? And I categorize them in performance, security, and then also extensibility. So I don't think virtualization is done at all. I think we have a lot more, actually. And so from a performance perspective, I believe that quality of service is critical to help solve the problem I described in the FDP scenario. I think that needs to be a throughout the drive rate limiting that's propagated. So that way, we don't have a situation with weighted round robins where this is a nice idea, but it ends up not propagating deeper than the submission queue fetch. We want to have the ability to have that performance limitation, performance control throughout the drive. So I believe QoS can help bring that through. The prioritization of one tenant over another, I wasn't able to catch the CDL conversation. That was HDD focused, but I think that there's a similar kind of use case where we need that priority of delivering I/O consistency in contrast to a rate limiting, right? This is a different type of behavior that's valuable for different types of tenants. From a security perspective, there's keeper I/O is there. To earlier question, when we're migrating data through the VM, when we're migrating data through the VMM, there's a potential where the data is migrated and it's unencrypted. And this is an exposure, right? So keeper I/O has the possibility of keeping the data encrypted during that live migration. I believe that, I'm not deeply ingrained with Caliptra and lock, but I believe there's a similar possibility that that might be closing that hole as well. But that's something that I think we need to just see out of them. Let me finish this slide. This is the last slide. TDISP, I already alluded to this. I think it's going to get extended. Deeper into the SSD is a possibility, enabling those boundaries and confirmation of status. And then I think there's extensibility of tenants, right? So defining a QoS tenant might enable a storage versus a namespace differentiated use cases, maybe using those submission queue groups rather than a controller. As NVMe right now, we're focused on more of a controller for tenants. And I think that SIOV is something that maybe could allow from tens to hundreds of tenants up through thousands and potentially beyond. And I think that's my last slide. So I did see a question where I can jump right to that, but otherwise I'm open for discussion.
So about the keeper I/O, so that is for encrypting data at rest, not in transit, right?
So let me repeat the question. There's a question, keeper I/O, clarification is that's focus is encrypting data at rest. And that's true. That was its focus, but it also has a standardized key generation method, which means that if it were that between two SSDs, we know how those two SSDs are going to generate their keys. And so if you leave data encrypted, you're able to migrate it and decrypt it on a different destination. So it has a standardized encryption method. That's the critical value add that I'm alluding to. You're right, it's not a focus of keeper I/O, so perhaps it's because I was subtly extending its intent from the original development.
So you're talking about being able to provide the key on the other SSD, which makes sense. You're not talking about protecting the data while it's in flight from one SSD to the other.
So to clarify, you use keeper I/O to encrypt locally at one SSD. You do not remove that key as you move the data from source to target. And since you know the generation methodology and can repeat it over on target, you're going to be able to decrypt over on the target.
But it's unencrypted while it's being transmitted.
It's encrypted, but it would not, there's not a standardized seed. So it would lack a seed, but it would have the key continue to apply through the data that's getting transferred.
So how would you be able to, so I thought the keeper I/O, I thought you had to provide the key on the read operation that you would use to get the data over to the other SSD.
Please, yeah.
Okay, so Randy's question is about the keys that are used to encrypt, and the TCG,
No. The question is about the data being
transferred.
encrypted while it's being transferred.
That's right. And the way Keeper.io works is we have this SSC defined in Trusted Computing Group where they inject the keys. Problem is that an implementation of a self-encrypting drive may have a unique key that sits at the very bottom and it is completely inaccessible to the outside world. One advantage of that is if you want to blow away the drive all in a single sanitize command, you just change that one key. Problem, though, is that there's no way to take that from one drive and put it on the other. So at some point, and I think this might have been what you're saying, you have to decrypt inside the source drive, re-encrypt with whatever that common is, get it over here, decrypt from that, and then re-encrypt at the bottom of some chain of derived keys using the unique key that's hidden inside the target drive. Okay, so you were talking about a decrypt, re-encrypt, transmit in a safe state. Okay, that's what I wanted to make sure you were saying.
So
Thank you, Paul.
VMM needs to be able to have access to that.
It's got to find a way of sharing that common key between the two.
Which it does, because the VM is aware of its key that it's using for key per IO.
Right.
And it is the same VM at the source and the same VM at the destination. So it.
That's not what I'm talking about. I'm talking about the VMM that is transmitting the data between the source and the destination.
So when the VMM is transmitting the data, there is, like Paul said, there's a potential seed. I have this one, thank you. There's a potential seed and potential in-drive encryption. Those would be stripped off. Leave the keeper IO key in place. The data gets transferred with only the keeper IO key in place. It gets written. The drive at the destination now has the option to decrypt and re-encrypt with its seed and its encryption key.
That's not what you said.
Yeah, that's a bit. I'm rewriting part of IEEE 2883 right now.
Oh.
And I'm trying to cover all these cases.
Thank you.
Jeff Anderson had some good inputs on that. But yeah, so I've got to figure that out, basically. And
So-
Jeff may have already figured it out, but yes, you have to, it's got to be protected when it leaves that first drive all the way across into the next one. So it's a question of how many keys you're going to have to deal with. So I'd say this is kind of an open thing.
Is the VMM privy to the VM's keys?
Good question. I don't know. I don't know what's been done in those.
My goal personally would be that the VMM is not, but I guess this looks like, this was intended to be a future. So it's not solved yet, I guess, is the major takeaway.
Yeah.
And I hear that I maybe oversimplified when I wrote this.
Yeah.
So this is, I also hear interest in actually having this work, so that would be great. Thank you, super appreciate that you came up to give more depth.
You need to join IEEE Security and Storage Working Group and help get us through this.
Yeah, good questions, thank you. Yes, please.
Actually, I was just going to remind you. I'm curious what the threat model is there, because if you're removing virtualization track, you have a VM that has to talk to the drive that has to be talking to your old drive, talking to the reinstantiation of the same VM, supposedly, to a new drive, right? So at some point you have to have, it's kind of like if you have the same VM, you have it.
Do you mind if we
Yeah.
go back to the picture?
Yeah, here, I'll do that and give you the speaker. The question was, what is the threat model? So I'm going back to the image, just here.
This is good.
This is good enough.
Yeah. So the point actually, do you have where it's transferring the data? That would be the best one. Yes, this is it. So the problem is that the VM has the key, or it has the key ID. The drive does have the key. We know that. But it's the VMM is the one that's copying the data over to the other side. And so this VMM, either it has to be privy to the key ID that this guy is using. That's one thing that needs to happen. And the other thing is that, as far as I understand it, there's no way to read without having the key. That you can't get you can't get encrypted data off.
Correct.
And so the question is this transfer, how are we protecting this transfer?
So, and my intent when I wrote that was that we did not remove the key per IO key and left it in place during the migration. That was my intent.
Yes.
But I'm also hearing that there's gaps that need to be solved in
Sure.
actually the success of this working.
Randy, your first question was the best one.
Okay.
Just ask your first question again, relating to.
Is the data unencrypted in order to get off the drive?
Is it data at rest or is it otherwise?
Yes. Is it the key per IO is data at rest?
That's
Yep.
my understanding, based on what I'm reading on the SNIA website.
Yep. Okay.
Yeah, one last comment. The thing that really complicates this, if you're trying to provide data in flight protection, meaning it's encrypted while it goes over, is that self-encrypting drives are expecting to receive plain text, unencrypted data. So we've got to dig into this.
Yeah, and I think that also, while I think we focused on key per IO, I think that I'm under the impression that there's some discussions along this line in Caliptra and Lock, so potentially they have other ideas, right? So, but yeah, really good discussion. Thank you for everyone joining in. Did I notice a question that popped up for a second?
Just answered the own question.
Yeah, go for it.
So as Dan presented here, virtualization is a complex problem, but the parts of virtualization solve other problems. That's one of the reasons why we had so many TPs. For example, he had the tell me what logical blocks are actually allocated in a namespace. Well, if you're doing snapshotting, it would be really nice to know that I'm going to just save data that was actually written, not save the whole namespace. So that's why it was carved out. Okay. We added that data queue because it made it easier, but there are plans in the future to do other types of, hey, drive, just send the guy some information so he could do some stuff. So as you think about this, I see some telemetry that can be pushed out without having to be asked live. And as you think of this, and I just wanted to say that when Dan brought up that last slide, he said, here's some potential areas that we could grow and think about this. Because right now, yes, NVMe only defines unencrypted data going across that. Should we think about how do we get encrypted data as we're migrating it? And that's just something, and yes, we would have to make a change in NVMe to do that, right? But as you look at all of these things that we've done here, a lot of different stuff is done. It was nice to break them up into chunks so we can get it through committee, but it's also think about all the possibilities that we can use those different parts for different things. Because when you look at all this virtualization stuff, it's the NVMe device providing services for the host to take advantages of those services. And we can use them for many different things. So as you can see, we have a lot of potential to do a lot more work in both SNIA, NVMe, and other organizations. So it's a lot of fun to work on. And virtualization, I'm having a good time with. So.
Yeah, thanks, Mike, for driving a lot of this through NVMe. And Paul, you had to further.
Yeah, Dan, could you go back to the one showing the transfer of data? So good enough. What I'm thinking is we may be overthinking this because ordinarily traffic between the drives and the host is not encrypted. So we have to analyze, is there a special threat in this migration that we do have to encrypt the drive, have encrypted data in flight?
Well, absolutely. Yeah. There's networks out there, and storage, we do great, but networks, we can't trust those, right?
Yes. Yeah.
Oh, so
Yeah.
comment so that later recording is TDIS potentially could be used to do the data transport
Right.
in motion. Yeah.
Okay.
Yeah, but that doesn't solve the source to target problem, right? You're talking TDIS is from the host to the NVMe PCIe file.
Yeah.
You want to repeat that?
I lost the summary. Yeah. Yeah.
Yeah, we're in futures.
Yeah, Michael had a.
You bet.
Dan, when we talk about performance, isolation, and virtualization, how do we describe and quantify the amount of isolation that a given storage system implements so that it can be compared and standardized across devices and also compared to the software implementation? Because I've heard the feedback that while pass-through to the hardware is advantageous for performance, the quality may not be as good as the software implementation. So how do we put those in numbers and look at them next to each other?
I think the simple answer is RGs per tenant. Defining an RG boundary should answer that, I believe. Unless I'm missing a part of your.
You want to do 1,000 of them?
But right now we're focused on VMs more like tens and hundreds, right? So, but RGs can be an answer to that. So that being said, I also, actually, one thing I forgot to say explicitly is that the cool part about all this is that we're getting a lot of feedback in NVMe and PCIe when things show up there. It's community driven, right? So if you see a better solution than my knee-jerk reaction here with RGs, I'm happy to hear that shaping as well.
So the reclaim groups, it's a media isolation, but how do you compare then the pass-through PCIe device to the software implementation in the hypervisor?
How do you compare the performances of those?
Compare the quality of the inter-VM or inter-tenant isolation.
How do we compare the inter-tenant isolation? So I think that, so focused on the media, pardon me, let me go back to the FTP. You're focused on the performance separation, right? Is that okay, so going back to just this one example of FTP, if we have boundaries of how much over-provisioning this tenant 3 can consume by setting a boundary of RG around it, then this one would be limited to not be, the OP can't grow. So this is what I believe is answering you, unless I'm missing, maybe we should continue this after.
Maybe one response I can give to this is this helps mitigate a lot of performance isolation, but it certainly doesn't make it go away. If tenant 3 is triggering a bunch of garbage collection, tenant 1 and 2, every time they do a read, are going to have to stall whatever garbage collection programs or erasers that are going on. And you'll see that. So, it's not going to go away. It's just going to get mitigated more.
Yeah. And we never absolutely, like, tenant 1 in an ideal world would be on an isolated SSD and just brought up you're gonna have other commands in flight. So there's gonna be some always nominal impact, right? So it's driving towards that ideal. Virtualized SSDs presenting as one SSD are never as good as just one single alone SSD, right? So we're trying to drive towards that. So that being said, when you're gonna share the drive no matter what, the hardware paths inside of an SSD are going to end up being better than the software emulation of the same, right? We have the ability to take that information now inside of the SSD and try and meet those initial goals that are now we have the information in the SSD to try, right?
Quick question, Dan.
We're out
slide
of time.
You got 90 seconds, but.
So
Can you go to slide 9 real quick? Your slide 9? I had a question around slide 9, so back up 2 more. That'll do. You have the VM crossing over into, the VMM crossing into each of the VMs, as opposed to it just strictly being the VMs are talking bare metal to the thing. Is that under the assumption, for example, you don't want VMs issuing certain admin commands like format, sanitize, or even identify device so you know what vendor it is inside of there? So does the standards or the vision today have the VMM intercepting all of that? Or is the drive itself going, no, I'm not going to allow you to issue a format command through this channel, or I'm not going to identify the device?
I think this is solved through the I can't remember the number, but the exported NVM subsystem is one example solution. Mike was presenting on that on Monday, so Mike can. Yeah. Thank you. Yeah, let's go to the hallway.
All right.
Thank you.